functions and the basic things there are the functions, one variable functions and the limit of one variable functions and sequences. So let's start with the basic one variable function, which I think you guys already know what a function is, but a function, a one variable function, especially the real valued one, is from R, real to R, a function where you will have, for a particular value here, you will have a unique value. So every X here would have a unique value here, and every X will have a value and it will be unique. So that's your function. So the first thing is the definition of a function, which is every X in the domain will have a unique value in R, which is the codomain. Then we have some kind of functions that we've studied so far. First is your polynomial function, where let's say it looks like this: fx is equals to x cubed plus 7x plus 5. This polynomial kind of functions. Then second is the general form looks like this: an x to the power n plus an minus 1 x to the power n minus 1. And a1 x to the power 1 and a naught. So this is the general form of a function, a polynomial function. Then second kind of functions that we've studied are the quadratic ones. So it's this, where you can write fx is equals to a x minus b whole square plus c. These kind of functions, where in particular you can take this as fx is equals to x square plus 2. And the third ones are exponential functions we've also studied. So these kind of functions, fx is equals to a to the power x. We're studying the types of one variable. So this is one variable. This is for one variable function. One variable means your function only involves x. So a two variable function would look like this. If you have a two variable function, it will be a function of two variables, x and y, and it will look like, it will look something like this: x plus xy. It could look like this, right? Where it involves two variables, x and y. So in that sense, the functions that we've studied so far and that we'll continue to study in this math one is they all are one variable functions, only involve one variable x or y or whatever, but the variable would only be one. So this kind of functions, and with this we've also studied like this one: fx is equals to half to the power x. And the fourth kind of functions are the log ones, where you can take fx to be log, let's say, base 5x. These kind of functions. What else? What other kind of functions have we done so far? And functions that we've not done so far in this course are the trigonometric ones, right? We have not done them. We have not discussed them in particular. So trigonometric functions, because you will be studying trigonometric functions in the next few weeks, next 2-3 weeks. Those are your sine functions, your sine x, cos x, tan x, and then cosecant x, cot x, and secant x, right? So these are your trigonometric functions, where these are the main ones, these ones, and the other ones are just the reciprocal of these. So cosecant is the reciprocal of sine, and secant is the reciprocal of cos, and cot is the reciprocal of tan. Reciprocal as in this: cosecant is 1 by sine x. So if we were to see, okay, and then we have monotonicity is something we've already discussed, but let's do it one more time here. Monotonicity of your function is either it's monotonic increasing, monotone increasing, or monotone decreasing. Monotone increasing means, I'm writing it in short, monotone increasing and monotone decreasing, where if your x1 is less than x2 and x1, x2 are in the domain of f, and fx1 is less than equals to fx2, then we say it's monotone increasing. And if it's the other way around, that is if x1 is less than x2, same thing here. And for this, it becomes fx1 is greater than equals to fx2, then it becomes monotone decreasing. That's what we call monotonicity. For example, if you have fx is equals to minus 2x plus 5, then this is a monotone decreasing function. You can check by plotting this thing. For now, this is a monotone decreasing function. How do we know this? We can simply see the slope of x, the sign of x. So the sign here is negative, which means your function is decreasing, right? So it will look like this. It's a straight line, but it's something like this. And if you were to look for an example of monotone increasing, you can take x cube. That's a monotone increasing function. The graph looks like this. And then we have tangent lines. So we'll not discuss what a tangent in general is. Let's just discuss what a tangent for a function means. So let's say if you have a function and its graph looks like this. Then a tangent line to a function at a given point. Let's say I'm choosing this point of this function's graph. This is the function's graph, fx. And I've chosen this particular point. Then a line which we generally call it as it only touches the graph. When we describe tangent lines, we describe them as a line that touches your curve only at one point. Like if you have a curve of this form, then at this point, a tangent line would be a line that only touches this curve at one point, and it touches and then passes. That's it. That straight line is called a tangent line to this curve, but we're discussing about tangents in general. So tangent to a function basically means a line that gives you the direction. So if you've chosen this point, then I want to know where my function is directed towards. Directed as in, if I have this function, then I know that at this point, it's directed in this direction, right? And at this point, it's directed in this direction. And at this point, it's directed in this direction. So these direction lines are called tangent lines. So if I have this tangent line that touches this point and then passes the curve is called your tangent line. At this point, it will be this thing. So this line it's doing two things. It's touching the graph at one point, but that's not important. The important thing about tangent lines is that it gives you the direction of your curve's flow. Like at this point, my curve is flowing in this direction. So that's what your tangent line gives you. So if I were to find the tangent line at this point, it will be this. And it touches the graph at this point, and more importantly, it gives you the direction. So tangent, rather than defining your tangent lines as it touches my curve only at one point, we describe it as at a given point, a tangent line to a curve at a given point, to a curve fx at a given point. Let me just say this point is x0 comma y0, or x0 comma fx0. So a tangent to a curve fx at point x0 comma fx0 is a line that gives you the direction of the flow of this curve at this given point. So at this given point, your curve is actually like the way we discussed it here, that at this point, the direction would be this. This tangent line is actually giving you the direction of flow at this point. So those are called your tangent lines. And it does not have to touch your graph only at one point. Let's say if your graph is this, That's a little misleading definition. If your graph is this, and if I were to draw a tangent at this point, then the tangent will be this, right? The tangent line will be this. This line will be the tangent line. But if I'll extend it, it's going to cut this graph at more than one point, right? One here and the second one here. So the important part of your tangent line is not that it touches your graph only at one point. In this neighborhood, though, in this small region, in in the vicinity of this point, in the closeness of this point, this line only touches your graph at one point. That's true, but its main purpose is that it gives you the direction of the flow of your curve. That means when I'm here at this point, where is my curve tending towards? Is it going this way? Is it going this way? Where is it going? That's the idea behind a tangent line. That's why we find tangent lines, to give you the direction of the flow of your curve. Is it clear so far?
Yes, ma'am.
Okay. And then we'll do trigonometric functions. Indeed, we have discussed trigonometric functions up, right? So let's write the definition of trigonometric functions here only, of sine, cos, and all. So your sine of x is basically if you have a triangle, a right angle triangle, whose this angle is this angle. Let's say it's theta radian, and then this is 90 degrees. So for those, I think this, you guys must be familiar with this, that this is called the hypotenuse. This is the one with it, the one covering this angle, the other line. This is called the base, and this is called the perpendicular, right? This one's the perpendicular. So the one which is opposite to this angle is the perpendicular, and the other ones enclosing it, this angle, the hypotenuse and base, right? So your sine x is perpendicular upon hypotenuse. That means this length, let's say if this is, and you can't choose them to be anything, right? If I've chosen P to be 2 and I've chosen B to be 3, then your H is already decided. You don't get to choose it. So this will be square of 2 and square of 3 added, right? So it's already decided. And this is P by H. So basically, let's say if I'm taking this to be 2, this to be 3, then this will be 9 and 4. This will be 13, right? So the square root of 13. Your H will be square root of 13. Then your sine x will become, or I should say sine theta, because I've chosen theta to represent my angle. So sine theta will be P by H. Your P is 2 units. H is 3 units. Sorry, H is square root of 13 units, right? Square root of 13 units. This will give me 2 by root 13 units. Or actually, your units get cancelled anyway. Okay. This will be your sine of theta. Then similarly, your cos of theta is given by base upon hypotenuse. So your base in this case is 3 and your hypotenuse is root 13. So this will be your cos theta for this triangle. And not for this triangle, the cos of theta, whatever this theta is also already decided in this triangle, right? So whatever this theta is, the cos of that theta is given by this. And then next up, we have tan theta, which is given by perpendicular upon base. So perpendicular here is 2 and base is 3. This will be your tan theta. And the other ones, cosecant is the reciprocal of sine. So it will be root 13 by 2. Then secant is the reciprocal of this. So it will be root 13 by 3. And cot will be the reciprocal of this. So it will be 3 by 2. These things and more important things to note here are okay, let's come to the graph of these first. So if you have, let's say your function is, let's say my function is sine x. Then the graph of x, let's first, before going to the graph and all, let's first come to the domain of this. So what's the domain of sine theta function? So the domain is minus infinity to infinity. You can choose any value here. Theta could be anything, right? Angle could be anything. So you can have the domain here is minus infinity to infinity. And what's my range? So the range of sine theta is, because simply because your hypotenuse is always greater than the perpendicular. This one, your hypotenuse is greater than both of these, right? Hypotenuse is greater than perpendicular to, and it's greater than base 2. So that's why your range is -1 to 1, -1 and 1 included. Right? So that's my range for sine function. And then we have for cos function. So it remains the same. It's the same thing. The domain of domain and range both of sine and cos functions is the same. So it is the same thing here. And then for the tan one, the domain is from minus infinity to infinity, and your range is also from minus infinity to infinity.
Ma'am, I have a doubt.
Yeah.
Sine theta, how is the range -1 to 1, ma'am?
When you take a triangle, what sine theta? Sine theta is the ratio of perpendicular to the hypotenuse of a triangle whose angle is theta, right? Whose this angle is theta,
Okay, ma'am.
right? So your hypotenuse is always greater than the perpendicular, right? This is always greater than this thing.
Okay, ma'am.
And this is also always greater than the base.
Okay, ma'am.
That's why this quantity, if your P is less than H, then P by H is going to be less than 1, right?
Okay.
That's why.
Okay, ma'am. Thank you, ma'am.
Then coming to,
Ma'am,
yeah,
but we consider a tan graph, it will be having some breaks in between, right?
yeah, it'll have breaks in between, but the range is still minus infinity to infinity, right? It covers everything on the y-axis,
The
right?
domain is not pi by 2, the tan x.
Yeah, it's okay. The domain part we have a problem at pi by 2, correct? So, or actually pi by 2, all the odd multiples of pi by 2, you can say, you can remove
N pi by
all
2.
multiples, or let me just write 2n plus 1 pi by 2 to ensure that where n is coming from natural numbers, right? Or integers you can take, that's fine. This one's fine. So you can't take the multiples of pi by 2 in the domain of tan. And your graph looks like this. So sine 1, for sine, it looks like this, where this is 0. You're taking the angles here. On the x-axis, we take the angles, and on the y-axis, right? This x is the angle. So on x-axis, we're taking the angle 0. Here we take pi. Then here we take 2 pi. And this one is pi by 2. This one is 3 pi by 2. One circle is completed till, okay, all the values have been covered till 2 pi once, right? So this is -1. The largest value it can take is +1. This one is +1. The smallest value it can take is -1. So all the values from -1 to 1 have been covered till 2 pi, right? And then everything starts repeating from here. 0 to 4 pi, everything repeats. It keeps going on like this, and the same goes here. This will be -pi. This will be minus 2 pi on this side. So this is the graph for sin x. Then we have the graph for, just 1 second. The graph for fx is equals to cos x, which looks like this. So instead you start from, at 0, the value is pi by 2. Sorry, at 0, the value is 1. So you have the highest value here, and then it decreases from here. The highest value is minus 1. Sorry, 1. This value is 1. And the lowest value again is minus 1. This is at 0. This is attained at pi by 2. This is at pi. This is 0. This is 3 pi by 2. This is 2 pi. So one round gets completed from here to here. And then everything starts repeating, right? This is 2 pi and this will be 4 pi here.
Madam,
This is the
one doubt.
graph. Yeah.
Why the x-axis is in like units is in pi? And what is the reason for that?
What?
No, y-axis we are keeping the range of the
Yeah.
x-axis. Why it is in pi?
Your x-axis is in pi because your angles, we discussed this here, right? When we were drawing the triangle and all, we said we take the triangle in radians, right? The angle in radians. So your theta is, the unit that you take for theta is, we generally take degrees too, but here we take radian. So, and your radians are in pi only. So pi is as in 3 pi, 4 pi, that's the usual way to denote angles in radians. So when we discuss angle in radians, it's usually in terms of pi and all. Is that okay? Okay. Instead of, so this is, if you're not, pi by 2 is the same as 90 degrees. So we take 90 degree to be pi by 2, this angle, this 90-degree angle to be pi by 2. And then 180 degree, the twice of this becomes pi. And then the next one is 270 degree, which is 3 pi by 2. And this becomes 360 degree, which is 2 pi. So this is pi by 2 angle. This one, which we call 180 degree. This one is pi angle. Then this one, this angle starting from here to here is 3 pi by 2. And then this angle starting from here and ending here is 2 pi, right? So that's how we convert from degree to radians. So we generally take angles in radians. That's why we have taken the x-axis, the unit of x-axis in radians, and we have taken pi here. Okay. Then the last graph was for fx is equals to tan x. And your tan x graph, because you've already seen that the domain cannot have pi by 2 value. So it looks like this. You have 0 here, then pi by 2. Then let's have pi here. And you will have 3 pi by 2 here and 2 pi, right? That's what we have been taking so far in the other graphs too. This will be it, the positive side, and the other side will just have negative values of this, minus pi by 2 and all, minus pi. This graph looks like at infinity. So when at pi by 2, your tan x tends to infinity. So tan x at pi by 2 tends to infinity. So it becomes this thing. And this one becomes this. One important thing that I should have mentioned when we were discussing functions only is I'll mention that thing here. When you see fx, when you have a function fx equals to, let's say y is equals to fx is a function given to you. And when you plot the graph of it, you say, let's say this is the graph of the function given. Then this distance on the x-axis gives you x coordinate, and this one here, this height gives you. So this function is basically the height at the point x, right? This height is what gives you the function's value. So if you were to find fx, or let's say fx2 or f3, let's say, if you were to find f3, it simply means that you have to find the height of this function, this thing at 3. So at x is equal to, let's say this is x is equals to, this is 1, this is 2, and this is 3. Then you have to find the height of this function at 3. That means from here, this distance is going to give you, this distance is going to give you f3, right? So f3 or fx in general is just the height of your function, right? Height from x-axis. It's the distance from x-axis at a given point x. That's one thing. So this is at x equals to pi by 2, your function goes to infinity. So it becomes, your graph looks like this. And at minus pi by 2, it's here. On the other side, it's going to minus infinity. So if you see a graph like this, it keeps going on like this. They're all in parallels to each other. They're copies of each other, even if I've drawn them slightly differently. So now let's just consider this line first. At x equals to pi by 2, I don't have a value, right? What's the height at x equals to pi by 2? I can't find the height because at pi by 2, you keep increasing as you come close to pi by 2. As x comes close to pi by 2, your function keeps increasing, right? So that means at x pi by 2, or as x comes close to pi by 2, your function tan x goes to infinity, right? It does not have a fixed value at pi by 2. It keeps increasing at pi by. When x comes close to pi by 2, when horizontally you come close to pi by 2, vertically, where are you moving? You're moving to infinity. That means your function does not have a value at all at point pi by 2. Okay. Then I'll just write some properties of these trigonometric functions here. The first property is the negation of argument. So if you have sine of minus x, this is the same as minus sine x. In cos, if you have minus x here, it will be cos x. And for tan, tan of minus x, it's minus tan x. Then sine square x and cos square x is always equals to 1 for all x belonging to real numbers. Then sin x by cos x is tan x. This is true. This is also true for all x. And we've discussed the reciprocal properties, right? That cosecant is the reciprocal of sine, secant is the reciprocal of cos. Then one more, although there are a lot of trigonometric identities, but I'll just discuss the basic ones. This is sine of 2x. When your angle is 2x, you can have the half angle here, sine x and cos x, and your 2 comes here. And fifth is of cos 2x, which is cos square x minus sine square x. So these are some basic identities that you should know. And then this quadrant rule too, where you have all positive here. That means if you have an angle here, let's say if your angle theta is equals to 30 degree and 30, this is 90 degrees, this is 180 degrees, this is 270 degrees, and this is 3. After completing a round, this becomes 360 degree, right? It's also 0 degree if you're just here, but if you complete one round, you'll get 360 degrees. So if your angle is here, if theta is here, let's say if theta is 30 degree, that means it's in the first quadrant, right? You're here. So then you have all the trigonometric functions positive here. So when your theta is between 0 and 90 degree, that means when your theta is in this quadrant, for this quadrant, all your trigonometric functions are positive. So in short, we just write all positive here. On this side, we have sine and cosecant positive. All the others are just negative. They are only these two are positive here. All the others are negative. If you have it here, we only have tan and cot positive here. All the others are negative. And on this side, we have cos and secant positive here. All the others are just negative. So this is what you should remember. So if you have theta is equal to 30 degree, that means all sine 30, cos 30, cot 30, all of them are positive. If you will have if instead you will have sine 100 degrees, then sine and cosecant, sine 100 degree and cosecant 100 degree would be positive and others will be negative. Right? And you can check the values of all these functions at the basic values, pi by 3, at pi by 2, pi by 6. I should have pi by 6. Here we'll have pi by 3 and then pi. You can check the values at these important important angles. These are considered important angles. You should know the value of all your functions, all your trigonometric functions there. We have a table for it. So you can learn the values from there. In general, we have discussed all the basic properties of trigonometric functions. And then we have composition of functions, but we've already discussed composition in 5th week, I guess. So we're not discussing it here again. And then we have graph of a function. So graph is basically, we know what it looks like. So we take x-axis, the Cartesian plane, and then we plot the graph of fx. But what does it mean? What does graph of a function mean? So graph of fx is it's a set basically where you collect these type of elements. So let's say x is where x is in the domain. So I represent domain of a function f as df. So I'll do that here. So if your x is in domain of f, then the collection of all the x fx will be, so let's say if your function is, you have a function which maps 1, 2, 3, 4 to 1, 3, 5, 7. Let's say this maps 1 to this, 2 to this, 3 to this, and this to this. This is a function, right? Let me just call this function f. Then what's the graph of this function? The graph of this function will be collection of all the points. So the first coordinate should be the collection of x here. And the second should be the value of the function at that point x, where x is in the domain, right? So your domain is 1, 2, 3, 4. This is your domain. This is your codomain. And in this particular case, your codomain and range are the same thing. Right? Your codomain is the same as range. But in general, it's not true. So let me just write codomain here. So if this is how your function looks like, if this is the mapping under your function, then what should I have here? I should have 1 here because that's the first element in your domain, and 1 is mapped to 3. So 1, 3. Then the next will be 2, 1. Then 3 is mapped to 5, so 3, 5. And then 4 is mapped to 7. So the collection of these points is called the graph of fx. This set is called the graph of fx, which is, if you can see carefully, it will be it's the subset of domain cross product or your Cartesian product of domain and codomain, right? This is for the Cartesian product. If I take the Cartesian product of D and your domain and codomain, then this set is going to be the subset of that set, right? Of the Cartesian product. So that's called your graph of a given function fx. Okay, so and then we can obviously plot this. So how do we plot this? We take the x, the first tuple, the first ones here on x-axis, and the second ones on this axis. And then it will be, let's say this is 1, 2, 3, 4. And this is, we have 1, 3, 5, 7, right? We can take this as 1, 2, 3, and 4, 5, 6, 7. And then you can plot this here. So at 1, my value is 3. So this point is in my graph. Then at 2, I have value 1. So this will be in my graph. Then at 3, I have 5. This point will be in my graph. And at 4, I have 7. So this will be 4 and 7 is here, right? So I've plotted all these points. And this collection of these points, this is the graph of the, now if I were to plot this functions graph, it's this, right? This is how you plot the graph of a function. Now let's say if you have a function fx, which is equals to x squared, then what does the graph look like? If I were to define it as a set, as we've defined it here, then what is the graph of this function? Let me call this gx. Then graph of gx will be, now I can't possibly write all the points here, right? Because here we only had 4 pairs, but in here we'll have a lot of pairs, right? So instead I'll write x fx, it's the collection of x fx, where x is coming from the domain, and domain in this case, the natural domain for this function is real numbers, right? So instead of domain of f, I'm just simply writing our real numbers. So this will be x, and fx is nothing but, sorry, I should have written gx here, right? This should be gx and this should be gx. So this will be x, and gx is nothing but x squared. So the collection of all the points of the form x and x squared would be my graph, right? And then if I'll plot all these points, it will be like this. At this point, you have to take 0 and square of 0. So it's this point. At 1, I can't possibly draw all the points here, right? So how do you, and the graph looks like this, right? The graph of x square is this. And in set form, it's this, where you take the x coordinate here and the y coordinate here. So this is your graph in set form, and this is what your graph looks like when you draw it on Cartesian, in Cartesian coordinate system, right?
Ma'am, could you please explain this one thing again?
See, we've seen how we plot graphs, right? If you have x squared, then the graph of x squared looks like this, right? So this is the graph of x squared. And what's this? Let's say this point is 1. Then what is this point? The point right above 1 on this graph, what is this point? If this is the graph of fx is equals to x squared, then this point is 1, 1, right? Now if I'll have 2 here, then this point here will be 2, 4. So what are we doing here? On this graph, what is this graph? This is basically the collection of all the points of this kind, right? X and x squared, right? We're just collecting them like this 1, 1, 1, 2, 4. Similarly, I can have, let's say this is -3. Then this point will be -3, 9, right? Although according to the graph, it looks weird because at this height we have 1, but that's fine. If this point is -3, then this point should be -3, 9, right? So what are we doing on this curve? This is the curve for fx is equals to x square, but we're basically just collecting the points of the form x comma x square, right? 1 comma 1, 2 comma 4, 1.1 comma square of 1.1, 1.0729 comma square of 1.0729. That's what we're doing in this graph, right?
Yes, ma'am.
This graph is just the collection of such points. So if I were to write it, instead of drawing it, shouldn't I be writing this set? This set, the collection of all set, the set of collection of all the points on this graph is this, right? So when you draw the graph, it looks like this, but when you have to write it, it's this thing, right?
Yes, ma'am. Got it.
That's it. Okay. Then the next thing that we have is so for our course, we only need the tangent to a curve to a function. We don't need, there are two, although this is not a part of your syllabus, but tangents are typically, we discuss them in two manners. One is where you talk about tangents and secants, where you say that if this is a curve or if this is something given to you, then the tangent at this point will be this, right? Where it only touches your this given thing at one point. That's one way to define tangent. And then we say the secant is a line which touches your curve at 2 points. But when you're talking about a function, we've already discussed this thing. A tangent only means when in context of functions, when we talk about tangents, its main purpose is to describe how a function is flowing. That's it. That's its main purpose. So if I were to describe a tangent at this point, then it will be this. And the more important part about this line is that it's giving you the direction of the flow of this curve, because at this point, your curve is flowing in this direction, whereas at this point, your curve is flowing in this direction. Both directions are different. So the tangent line, the entire purpose of a tangent line to a curve or to a function is to describe where your curve is flowing. In which direction is it flowing? Now let's say, so for the course, please try to look at tangent lines as a line which gives you the direction of flow of your function instead of looking it as a line which only touches it. That's also true, but with a line, don't look at it as a line which only passes through your function at one point. That's important where we discuss geometry, and we're not studying tangents in context of geometry. We're studying it in context of functions. So here the purpose of a tangent is to describe the flow of your function, the direction of the flow of your function. Let's say if I'm taking the function fx is equals to, let's simply take x. Now this is a function. If I were to draw the tangent line to this function, then it will be, you will study tangent lines in detail in week 8, I guess. So we'll not do it here. So I'll just give you a little idea of what tangent lines are. So if your fx is equals to x graph looks like this, right? It passes through 0, 0 point. And it's a straight line. It looks like this. This is the graph of your fx is equals to x function. Now, if I were to find the tangent to this graph, if you will go by the definition that we use in geometry, which says that your tangent line should only be touching your graph at one point, then by that logic, you wouldn't have a tangent line to this graph, right? Can you have a line that only touches this curve at one point? Let's say at this point, I want a line which touches and then crosses. That's it. So the tangent line to this curve is the line itself. If you were to find a tangent line to this line, then it's this line itself. Because and why is it so? Because the main purpose of tangent lines in context of functions is to describe the flow, the direction of flow of your function. So if I were to find the direction of flow at this point of this function, then where is it flowing? It's going there, right? In this direction. So the line that gives me the flow of this function is this line itself. You will see, and later when you will study tangent lines, you will see that the tangent line to fx is equals to x is fx is equals to x. This is the tangent line. Tangent line is fx itself. Because fx itself is giving the direction of the function fx is equals to x. Okay. Now let's do this one. One more example where you have this thing. We'll take mod x function where you have this and this. This is what your mod x looks like. Now at this point, I know where my curve is flowing, right? It's flowing in this direction. So the tangent line is this line. So at x is equals to, let's say 1, tangent line is fx is equals to x. Or you can just say y is equals to, a tangent line here is given by y is equals to x. At x is equals to -1, tangent line is given by y is equals to -x. But at this point, if you were to define, you don't have to worry about these lines. You will see how you get the tangent lines later. You learn how to find them. But for now, I'm just giving you an example where I'm trying to show that at this point, you have a tangent line because you have a line that gives the direction of flow of this curve at this point. But if I were to choose this point, your 0, 0 point, then what's the direction of flow at this point? So because there's an abrupt change, can I say this is the direction? Because it's not going here, right? After this, and I can't say this either because there's an abrupt change. That's why there is no tangent at this point. Or in simple words, you can say when you have abrupt changes in your curve, you do not have tangent lines there. So if you have something like this, or if you have something like this, then because you have an abrupt change here, you are going here, and then suddenly you change the direction of the curve. That's why you do not have tangent lines at these points. One more example to look into is this one. The greatest, the the floor function, fx is equals to this. So if this is your function, then it will be this, right? From 0 to 1, this point is not included. So for all the values between 0 to 1, your function's value will be 0. Then from all the values between 1 to 2, this is, let's say, 2 point. This is excluded here. The function's value will be 1, right? Because this height is 1. And it goes on like this. This excluded, this included. Keeps going on like this. This is 0.2, this is 0.3, this is 0.4, and so on. So I know that there is a tangent at this point exists because you can decide the direction here, right? There could be a line here which gives you the direction of this curve, but there's no line here because there's an abrupt, this is not even abrupt change. It's like there is no function. It has jumped from here to here because the function has turned discontinuous. That's why you do not have a tangent anywhere. So anywhere, in short, if you see your function breaking somewhere, or if you see that your function has abrupt changes, like if we were to brief it all, it will be if fx has abrupt changes in direction, or jump at a point, or you can say discontinuity, or your graph becomes discontinuous. When we use discontinuous, we're using this term in a very loose sense, not in its literal sense, not in the definition sense. We're using it in loose sense here. So if your graph abruptly changes its direction, like in this one, or if it jumps from some point to the other point, because we have a break here, right? Jumps, or you can say if there is a break in your graph, I should write if your graph has a break. Then it does not have a tangent there. At, let's say, x, if at x point, like in this one, at point 2, your function suddenly jumps from here to here. At 3, your function jumps from here to here. So you have a jump at point 2, a jump at point 3, a jump at point 1. That's why all these points, you do not have a tangent. Then we'll discuss limits. Let's first discuss what a sequence is. So a sequence is basically the collection, this collection where you take A1, A2, A3, and it keeps going on. Like here you will have A100, and then later on you will have A1000, and then later on you will have A10,000, and keeps going on. Something of this form is called a sequence. Now, if I'll assign numbers to these, let's say I'm saying that I'll assign numbers like 1, 2, 3, 4, and it keeps going on like this. I know the pattern, the further pattern, it will be 5, 6, 7, 8, 9. So my A1 then is 1, A2 then is 2. This is called a sequence. Again, I'm not giving the proper definition here. We don't have time for that. So this is a sequence. Then I can, next up I can take 2, 5, or let's take -1, -10, -20, -30, -40, 45, 57. I don't know what next numbers are, but I know that it keeps going on. We have numbers further here, and they never end. This list will never end. This is a list which will keep going on. You don't have an end to this list. This is again a sequence where A1 is this term, A2 is this, A3 is -20, A4 is -30, A5, A6, A7, and it keeps going on till A 1 lakh, and then it keeps going on. So this is called a sequence, right? One more example that you can take is, let's say, so if you were to define a sequence, if you want a formal definition, it's simply f, a function from natural numbers to real numbers. If I say a real valued, a real sequence. So a sequence of real numbers, which is what you're going to study. So a sequence of real numbers is basically a function from n to r. Do you see this is a function where it will be, your first term will be f1, second term will be f2, third term will be f3. So let's say I'm taking this function to be 1 by n. Then f1 becomes 1, f2 becomes 1 by 2, f3 becomes 1 by 3, so on, and keeps going on, right? Because natural numbers never end. So this will be, what's my sequence then? If I have to write the sequence there, it will be 1. Then 1 by 2, then 1 by 3, then 1 by 4, and so on, right? Will never end. The collection of all these values will be your sequence. This is what we're writing as an, right? We said here we define it as a1, a2, a3. So this is the same as a1. I can call the value of f at 1 to be a1. Then I can call this to be a2, this to be a3, right? Let's do one more example of a sequence. Let's take Fn is equals to n square. Then my sequence will be 1. At 1, you have value 1. Then at 2, you will have value 4. Then at 3, you will have value 9, 16, 25, 36, 49, and so on, right? So this is again a sequence. So all of these things are sequences. Then let's come to the convergence. What do we mean when we say a sequence is convergent? So this is a list which never ends, right? So I know that this list, first thing is this list never ends. And where is this list going? If you look at this list carefully, it keeps increasing, right? I have 1 first, then 4, then 9. Each time your value is increasing, which means it never stops growing. That means it will cross every value. If I have a bound 100, then it will cross 100 because 11 square is 121. If I have a bound, let's say 1 lakh, then some number square is greater than 1 lakh, right? I can have a number whose square is greater than 1 lakh, right? So in simple, you can just simply take this number. If you take this number, the square of this number is greater than 1 lakh. So this does not have a bound. Bound means it does not stop anywhere. So that such sequences are called unbounded sequences. That means this sequence will go till infinity, right? Any sequence or any set, anything which does not have a bound, that means if it keeps growing, like if this is a function, we say that when x tends to infinity, when x grows without a bound, then y also, your height is also growing without a bound, right? Because it keeps increasing, it will keep going further. So y tending to infinity basically means that this value of y does not have a limit, it can keep growing. Okay. Then we'll talk about convergent sequences. Or when do we say a sequence is convergent? So let's say if I have a sequence an, right? An will be, it's the collection will be a1, a2, a3, and so on. Then I say that the sequence an is convergent if it keeps coming closer to a particular point. That means let's fix a number L. And if I say that an keeps coming closer as n increasing, if I'll move here, my n is increasing, right? It's 1 here, 2 here, 3 here, then it will be 4, then it will be 5. So as my n goes to infinity, that means then I say as n tends to infinity, where does my an go? So when n is going to infinity, this means when n keeps increasing, what happens to an? Like we saw here, when my n keeps increasing, what happens to this list? It also keeps increasing. So when n goes to infinity, this list, that is n square, is also going to infinity, right? This collection also goes to infinity. Does anyone have a doubt? It feels like do we have any doubt anywhere? Does anyone want to ask anything?
No, ma'am.
Okay. So a convergent sequence basically means this number as n keeps increasing. When I say n tends to infinity, this symbol means your n keeps increasing till infinity. Till infinity, that means it keeps increasing without a bound. So if n keeps increasing without a bound, where does my an go? What point does it become close to? Does it stop somewhere? Does it become close to something? So if I were to have a function, let's say let's understand this with an example. Let's say I have, so as if my n tends to infinity and an becomes closed, this is the simplest definition of a limit of a sequence or of convergence. If an becomes close to So for as n tends to infinity, an becomes close to a. This implies an, limit of an as n tends to infinity is a. So let's do an example here. Let's say you have 1 by n. Now my 1 by n sequence is this: 1, 1 by 2, then 1 by 3, then 1 by 4, and so on, so on. So as my n increases, for n is equals to 1, you have 1. My an is 1. For n is equals to, let's say, 10 lakh. My an is 1 by 10 lakh. For n is equals to 10 to the power 20. My an is 1 by 10 to the power 20. That means as my n keeps increasing, my an, this becomes 0.00001. This becomes 0.000 so many times. And then 1 here, right? That means this keeps becoming smaller and smaller. It keeps becoming smaller and smaller as my n keeps becoming larger, which means, and it will never be less than 0, right? So as n tends to infinity, my 1 by n comes close to 0. Graphically, here, if you will plot these points on x-axis, you don't need the y-axis here. It will be like this. If this is 0, then you will have 1 here, 1 by 2 here, then 1 by 3 somewhat here, and then it goes like this. So it keeps coming closer to 0. Each time you increase your n, it keeps coming closer to 0. That means your limit is 0. Okay. Then let's do this one. Let's say you have an is equals to 1 by, not 1 by, let's say 1 by n square. So what will happen to this? Same thing happens there. You will have 1, then 1 by 4, then 1 by 9, then 1 by 16. And if you notice, this is again going to 0, right? Each time it keeps becoming smaller and smaller and smaller. So it again goes to 0 as n tends to infinity. So as n moves to infinity means as n keeps increasing, your sequence, these terms move to 0. They become close to 0. And let's take this one. An is equals to minus 1 to the power n. Where does this go? This sequence is basically minus 1, then 1, then minus 1, then 1, then minus 1. Do you think this becomes close to any point as my n keeps becoming larger? Does this become close to any point?
No, ma'am.
This is 0. You have 1 here on this side, minus 1 on this side. So you have a1 here, then sorry, your a1 here, then a2 here, then a3 here, then a4 here. That means it keeps fluctuating between these 2 points. So it's not close to, it's not moving to any point. It's not moving to 1 and it's not moving to minus 1 either. Keeps fluctuating between these two. But if I have these separated, if I'll have a subsequence, we have not done subsequences, right? So your subsequences are basically, if an is a sequence, let's say if this is your sequence a1, a2, and a3, and so on, so on. Then a subsequence is basically the collection of the points. A subsequence is a subset of this only. If this is your set, then a subsequence is a subset of this, where you collect them in a specific order. So if I've chosen a2, then I should be, if I've chosen the first term of your subsequence to be a2, then the next that I should be choosing is something Either I should choose A3, A4 or something greater than. That means the next one, I can't choose A1 here. That, or in simple words, if I were to if I were to take a subsequence of this, I can take A2. And then the next term that I should be taking is after this A2. I should not be taking terms from here now. So I can take A5 then. Then I have to take something after A5. So I can't take A4 here. This won't be a subsequence. I can take A7, and I can take A10, A20, A30. This is fine. Just keep going on in this order. Now you suddenly cannot have A3 here. That will be incorrect. Is that okay? So a subsequence is basically you have to pick points from the sequence only, but in this specific order only, in this order. So I can pick this one, then I can pick this one, then I can pick this number, and I can write them in this order here. That's your subsequence. Now, if I were to make subsequences of this, can I say that one, this term, then this term? So all the even terms, the second term, fourth term, sixth term, if I'll collect all those terms here, I'll get 1, 1, 1, 1, right? So this is a subsequence of this, right? This is subsequence of AN. Can we say something about the convergence of this subsequence of AN? This one. Does this one converge? Do you think it's going somewhere? As my N keeps growing, as we keep moving forward, do you think this is going somewhere? This is becoming close to some point. This one's becoming close to 1, right? Because you have repeated 1 term there, 1, 1, 1, 1, 1. So this is going to 1, right? Similarly, if I take subsequence, another subsequence of AN, where I'll collect odd terms only. So it will be -1, first term, then third term, then fifth term. This will go to -1, right? But this is not going anywhere. So the sequences, these kind of sequences which do not go anywhere, these are called divergent subsequences. So divergent sequence is simply a sequence that is not convergent. Then we have some important limits. Let's have a look at them. The first one is this, summation x. Let's say I have this, x to the power k by, not x to the power k, let's take this, x by 2 factorial, x square by 2 factorial, then x cube by 3 factorial, or not this one, not this sequence, this one. Let's say I have x, then x plus x square by 2 factorial, then x plus x square by 3 factorial, x cube. Sorry, we're adding these, right? So we'll have x square by 2 factorial, x cube by 3 factorial. Then next time we'll add the fourth term too. So this will become x plus x square by 2 factorial plus x cube by 3 factorial and x to the power 4 by 4 factorial. And it keeps going on like this. Now, if I were to fix this thing, let's take this for x is equals to 1, or let's take this for x is equals to, yeah, let's take it for x is equals to 1. So I'll have 1 plus 1 by 2 factorial, then 1 plus 1 by 2 factorial plus 1 by 3 factorial, then 1 plus 1 by 2 factorial, 1 by 3 factorial, 1 by 4 factorial, and so on. Now this is a sequence, right? This is a sequence whose first term is this, second term is this, third term is this, and fourth term is this entire. It keeps going on, right? So I can simply write this as an is summation. My first term is first, so how should I write this sequence? My an is basically 1 plus 1 by 2 factorial plus 1 by 3 factorial plus so on plus 1 by n factorial, right? This is an. If this is a1, this is a2, this is a3, then your an is this. So I can write an as, an means the nth term of my sequence. Like the nth term of your sequence 1 by n. This is your sequence 1 by n. But what's my second term for this sequence? It's 1 by 2, right? So similarly, here, your nth term for this sequence is this. And how can I write this? I can write this as 1 by n, or I should write this as 1 by k factorial, k varying from 1 to n, right? So in such way, we define one sequence here, which is this one. Summation x to the power k, k factorial, where x is a fixed number. You can choose it to be 1. We chose it to be 1 here. And we missed 1 because it's starting from k is equals to 0. The sequence that we discussed was starting from k is equals to 1. Okay, let's forget that too. Let's say, okay. So add 1, 2 here. You can take x to the power 0 by 0 factorial plus x to the power 1 by 1 factorial. And this will be I can simply write this as 1, right? And then the next thing here will be 1 plus x to the power 1 by 1 factorial. Then you will have 1 plus x square by 2 factorial. We have just added 1 everywhere because this is a special kind of sequence which has a special limit. That's why we're discussing this one. So here you will have 1 added everywhere. And this will start with 1. So your first term is this. For an, this will be a1, this will be a2. Or you can say okay, let's not get into a1, a2, a3 and all. We've seen that thing. So then if I have to find the nth term here, I'll have, let's leave this out of here. We'll discuss it later. It's fine. Let's not make any changes still here. So a special kind of limit that we're doing is this one, where let's say your sequence is this instead of this one. Let's say I choose my sequence to be an is equals to summation 1 by k factorial, k varying from 0 to n. If this is what I'm choosing it to be, this is, what is this? This is 1 plus 1 by 2 factorial plus 1 by 3 factorial plus so on till 1 by n factorial. And what is this? This is 1 plus 1 because this first term will be 1 by 0 factorial, which is just 1. And then you'll have 1 by 1 factorial, it's again 1. So this is 1 by 2 factorial. This sequence, if you'll take this sequence, then the limit of this is an. You have to remember these limits. So I'm writing this for you to remember. This goes to 1 to e to the power 1. E to the power 1, or you can simply write this as e. This goes to e as n tends to infinity. So when n tends to infinity, this one goes to e. Or if you were to generalize this, this was when you took x is equals to 1, right? Now instead, if I'll take an is equals to summation x to the power k by k factorial, k varying from 0 to infinity, then what is this one? This is simply x to the power 0 by 0 factorial. So it's 1 plus x to the power 1 by 1 factorial. So it's simply x plus x square by 2 factorial plus xn by x to the power n by n factorial. This will be your nth term. So if I decide to take the sequence as this, as summation x to the power k by k factorial, k varying from 0 to n, this is a sequence. So my nth term will be this. What's the first term here? Or let's not find the first one. For example, my third term will be 1 plus x plus x square by 2 factorial and x cube by 3 factorial. This is my third term. Similarly, this is my nth term. And what does this converge to? This one. This summation xk, k factorial, k varying from 0 to n. This goes to e to the power x as n tends to infinity. Right? You have two things here. One is x and the other one is n varying. So as n tends to infinity, this entire sequence goes to e to the power x, depending on x. Like we discussed it here. If you will choose x is equals to 1, an will go to e to the power 1. If you will choose x is equals to 2, then this sequence will become 2 to the power k by k factorial, k varying from 0 to infinity, 0 to n. This sequence will go to e to the power 2. And this is true for all x. That means if I'll choose x is equals to 2, this sequence will go to e to the power 2. If I'll choose it to be 2.1 to the power k by k factorial, k varying from 0 to n, this sequence will go to e to the power 2.1. Similarly, we have other things. So the other one is 1 plus x to the power n whole to the power n. This sequence converges to e to the power x2. This also converges to e to the power x for all x belonging to real numbers. That means your 1 plus 1 by n to the power n, this thing, this sequence converges to e to the power 1 or just e. Right? Then the next one is the sequence n square root of 2 pi n by n factorial whole to the power 1 by n. This sequence converges to e. This is pi. This sequence also converges to e, and we have one more sequence that converges to e, which is this one. N by square root of n factorial, the nth root of n factorial. This is nth root of n factorial. This also
Yes, ma'am.
converges to e. Yeah.
Ma'am, could you please slow down? You're going too fast.
Yeah. Okay. These are just limits. So these things are something. This is what you have to learn. That's why I was
Yes.
going fast, because there's nothing to understand. This is just a limit that you should know, that the limit of this sequence is e to the power x. And this is a particular example of this one, right? I've put x is equals to 1. So this one should be e. and you don't have an x here. So this is simply a sequence which is going to E.
Ma'am, I have a question.
Yeah.
Is this covered in our week videos?
Weak videos as in the lectures that are there on portal.
Yes.
It should be there.
Okay, thank you.
Okay.
Ma'am, once can you zoom out so that we can take a screenshot for the properties?
Ma'am, I was saying to slow down because it takes time to write and grasp. So if you could really
Yeah, okay.
go a bit slow, that would be nice.
These are the properties, I guess these are all of them. And then there was one more, which is up there. So I'll write it here. It's summation x to the power k by k factorial, k varying from 0 to n. This is a sequence, and this converges to e to the power x. So all in all, these are the limits that you should know. Is this okay?
Yes, ma'am.
Okay.
I just have one question here.
Yeah.
Previously, you did not want to name them A1, A2, A3, but you were comfortable taking A3 as, if I'm not wrong, 1 plus x by x factorial.
This one?
Yeah, that is the one.
Yeah.
Right. But then is there a reason why you don't want to name it A1, A2, A3? But because in that case, A3 was not 1 by 3 factorial or x cubed by 3 factorial.
What happened here was that we wanted this sequence, right? I wanted to discuss this sequence, summation 1 by k factorial, k varying from 0 to n. But instead, I discussed this one where your k is varying from 1 to n, right? So it changed everything. And that's why I wanted to incorporate this sequence, summation 1 by k fact. How is this one different from this one? Here you have 1 plus 1 plus 1 by 2 factorial. This will be the second term, right? So
That's
A2
correct.
here will be this, and here A2 will be 1 plus 1 by 2 factorial. Now this one is, if you want to find the limit of this, if the limit of this entire thing is E, then obviously the limit here will be E minus 1. But because I wanted to discuss this one, so first I thought I'll just add 1 here everywhere.
Okay,
Here,
yeah.
but then I just removed it. That's
Okay.
it. So no particular reason at all. Okay.
But just it could be a basic question, but since there is in this case where there is 1 and then another 1 before it becomes 1 by 2 factorial, it's still a sequence because
Yeah, this is a sequence. If you have to write this, you can write it as, if you want to write this sequence as, just 1 second. You're talking about this one, right? 1 plus 1 plus 1 by 2 factorial. The next term will be 1 plus 1 plus 1 by 2 factorial and 1 by 3 factorial, right?
that's correct.
And it keeps going on like this. So this is a sequence, is basically a collection of numbers. That's it. Which keeps going on. This collection keeps going on. That's it. That's what a sequence is. So I can take 1, 10, then minus 10, then 20, then minus 30, then anything that I want.
Fair.
So
fair, thanks.
any collection, but it has to be a countable collection. I don't want you to be confused with countable and uncountable and all. That's why we say it's a function from. That means its indexing is this thing that you have here, right? A1, A2, A3. This is called indexing, right? So this indexing should be from natural numbers. That's our concern. That's it.
No, which is fair. I think you already mentioned this
Yeah.
when you started. Yeah, thanks.
Okay. So then moving on, we have some rules for limits of sequences. Let's say you have an, and an is going to a. An converges to a, and let's say bn converges to b. Then first thing is, what will be the sum? What will the sum converge to then? This should converge somewhere. or should it, so this will converge to A plus B. So if AN is going to A and BN is going to B, then AN plus BN, this is also a sequence, right? You're just adding corresponding terms of AN and BN sequence. This is also a sequence. This will go to A plus B. And second is if you do AN minus BN, this should go to A minus B. So for example, let's say you have, if you want examples of this, we can do that too. Let's say you have a sequence minus 1 to the power n by n minus 1 by n. Let's say this is our sequence. The nth term of our sequence is given by minus 1 to the power n by n, or let me just take a positive sign here and a negative here. Let's see how our terms look like. They look like this. First term will be 1 minus, you'll have a 1 here, so it will be minus 1, right? So this will be 2. Why shouldn't be taking this thing? I should instead take this. So if this is my sequence, this will be 1 minus 1. This is, yeah. So your first term will be 2. Then your second term will be, if I'll put 2 here, I'll have 1 by 2 plus, we have a 2 here, so this will be 1 by 2, right?
Ma'am,
What happens is, yeah,
I think A1 should be 0.
you have 1 here. We'll put 1 here and then we'll put minus 1 to the power 1, right? Yeah, it's 0. This one's 0. Or in this one is 0. The second one gets added, so it will be 1 by 2 and 1 by 2. The third one will again be 0. Fourth one will get added, so this will be 1 by 4 and 1 by 4. So what's happening here is, this is the pattern, right? What's happening? Your AN is actually 2 times 1 by n. So this will be 2 by n when your n is even, and 0 when your n is odd, right? This is your sequence simply. So it's this 0 and 2 by n, or this is how I can write my sequence, right? Now, where is this thing going? It's this, the odd terms, if you look at the odd terms, they are just 0, 0, 0. So at odd positions, you just have 0, 0, 0. That means this is going to 0. Now let's come to the even ones. You have 1 by 4, the second position. At second position, you have 1 by 4. At fourth position, you have 2 by 4, which is 1 by 2. Then at the sixth position, you will have,
In second position, we have 1.
okay, you will have, yeah, at second we have 1. At second we have 1, and at the first we have half, right? The next one is half. And then the next one will be
1/3.
1 by, it's 1 by 6 and 1 by 6, right? So it will be 1/3, right? And then the next one will be, so if the pattern that we're moving in is this 1 by 2, 1 by 3, 1 by 4, 1 by 5. So it's again going to 0, right? So these are odd terms of AN. That means these are A1, A3, A5, and all of these terms. And these are even terms. And your even terms are going to, these are A2, A4, A6. They're also going to 0. That means your entire sequence consists of only odd and even terms, and all of them are going to 0, right? That means your sequence is going to 0, right? So, and where is this one going? If we look at these individually, let's say this is sequence Bn and this is sequence Cn. Then Bn is 1 by n and it's going to infinity 0. This is going to 0 as n tends to infinity. And Cn is minus 1 to the power n by n. Where is this one going? This is minus 1, then 1 by 2, then minus 1 by 3, then 1 by 4. Where is this sequence going? If you
Zero.
again, yeah, it's going to 0, even though it's fluctuating here. For sometimes it's here. So for the odd terms, it's on the negative side, or for the even terms, it's on the positive side, but it keeps coming closer to 0, irrespective of the sign, right? So if you take the odd terms, you will have minus 1, minus 1 by 3, minus 1 by 5, and so on, so on. If you will take the even terms, you will have half, 1 by 4, 1 by 6, and so on, so on. This thing is also going to 0, and this thing is also going to 0. And because this sequence consists only of these ones only, right? It doesn't have any other point that we have forgotten. That's why this will also go to 0. This is going to 0. That means your Bn is going to 0, Cn is going to 0. So the sum of these two should also go to 0, right? Sum of these two is An. This is also going to 0. This goes to 0. This also goes to 0. So An also goes to 0. Same happens here in this case. Then the third one is for the product, if you have An and Bn. And An was going to A, Bn was going to B, then An, Bn goes to AB, the product. An example you can take here is 1 by n, take An to be 1 by n and Bn to be 1 by n again. This will give you your A and Bn then will be equal to 1 by n square, which also goes to 0. And then the fourth one is An by Bn. This goes to A by B, provided B is not equals to 0. So we want this thing to be given to us that B should not be equal to 0. So if B is not equals to 0, then my An by Bn sequence is going to A by B. For example, you can take An to be 1 by n plus 1, Bn to be n. Then your An by Bn is 1 by n plus 1. And this is going to 0, right? Because An was going to 0, and where was Bn going? Bn was going to infinity though, but when you have 0 by infinity form, you can just simply write this as 0 by 0 form, right? 0 by infinity form is equivalent to 0 into 0 form, which is just 0. So that's why, or if this does not look a very nice example for this one, the quotient one, let's take some other example. Let's take An to be 2 plus 1 by n. And let's take Bn to be 3 plus 1 by n square. Then where is An going? We have seen this goes to 2, this goes to 0. So the sum should go to 2, right? So An goes to 2 and this sequence goes to 3 because this one goes to 0. And this one, this sequence goes to, this is a constant sequence, right? 3, 3, 3, 3. And this goes to 0. So An by Bn then will be 2 plus 1 by n and 3 plus 1 by n square. This should go to 2 by 3 as per this rule. Is this okay? Okay, the next property that we have is this one. If An is converging to A, we've already written it. So your C times or a constant times An goes to constant times A, where K is a constant. Which means if An is going to, let's say 5, then 3 times An will converge to 15. Similarly, if you have an going to a, then k to the power an will go to k to the power a. That means if your an, let's say, is converging to 7, then e to the power an, where your e is 2.71, this irrational number, or let's not take e to the power an, let's take 3 to the power an. So 3 to the power an then will converge to 3 to the power 7. And finally, we have if your an is converging to, we have log 1 then. But for that, we need specific other things too, right? If you're saying that an is converging to a, then can I say that log an will converge to log a, or would I need some things to make sure that this thing is valid, right? What conditions do I need to make sure that my log an, let's say the base is c. If I've chosen the base to be c, then what do I need to make sure while claiming this thing, that if an is converging to a, then log an is converging to log a? What do I need to make sure? First thing is c should be, your base should be greater than 0 and your base should not be equal to 1. So we've discussed this thing, right? When we were studying log functions, we have discussed that the base should be greater than 0. Then the other thing that we want is your an should be greater than 0, right? So whenever you take the argument of a log function, log x, we want x to be greater than 0, right? So that condition stays here. That means if you're taking an, now let's say if I have a sequence -1 to the power n by n, this is a sequence, then log of -1 to the power n by n, this is not even valid, right? This sequence, if I'm calling this bn, this sequence is not even valid, because at n is equals to 1, you will have log of -1, which is not correct. -1 is not in the domain of log function. So that's why we need to make sure that this thing an should be in the domain of log functions, that function. That's why I want an to be greater than 0, right? This is what you need to make sure. If this is true, so if c is greater than 0, c is not equals to 1, and an, all these terms are greater than 0, then I can say, or eventually, even if they are not greater than 0, that's fine. Okay, for now, you just keep in mind if all an terms are greater than 0, then log an will converge to log a. Is this okay? So if at any point you guys feel that this pace of the lecture is too fast, you can unmute yourself and let me know. Okay. And then last property that we have here is your sandwich principle, which says that if an is converging to, let's say an is converging to a, and bn is also converging to a. So we have two sequences now that are converging to the same number a. And let's say cn is a sequence which is between an and bn. So this is a sequence which is converging to a. This is also a sequence converging to a, and cn. That means c1 lies between a1 and b1. c2 lies between a2 and b2. This is what it means. And so on, so on. So this should mean that your cn also converges to a. So if cn is sandwiched between two sequences that are going to the same number, then cn is also going to that same number. For example, let's say you have 1 by n square, right? So 1 by n square is for natural numbers, because when you take a sequence, n is always a natural number, right? So can I just say that 1 by n square is less than 1 by n? It's true for natural numbers, right? This is 1 by 2 because n square is greater than n for natural numbers. That means your 1 by n square should be less than 1 by n for natural numbers. This is only true for natural numbers. Not only true, but we are talking about natural numbers. So it's true for natural numbers. And 0, because this is 1 by n square. So 1 is positive, n square is also positive. That means this entire term, 1 by n square, no matter what n you choose, is always greater than 0, right? That means I can choose 0. That means your 1 by n square is sandwiched between two sequences. One is 0 sequence and the other one is 1 by n. It means 1 is, for the first one, it will be this. For the second one, it will be 1 by 2, 1 by 4. And for the third one, it will be 1 by 9, 1 by 3. That means this always lies between these two. Now, this sequence, constant sequence 0, 0, 0, this goes to 0. And this sequence 1, 1 by 2, this also goes to 0. And 1 by n square is sandwiched between these two. This means 1 by n square should go to 0, right? So a 1 by n square also goes to 0. Then finally, we have limit of functions. So let's do that. Let's say you have a one variable function, fx. And the limit simply here means that if your x is going to some point, let's say a is a point, a is any number, and x is converging to a. That means if x keeps getting close to a, then what happens to fx? Where does my fx go? Graphically, if you look at this, let's say if this is a graph and this is point A. Now, if I say x keeps coming closer to this point A, then my graph, where does it move? We have height. At this point, we have this height. At this point, we have this height. So it will move to this point, right? So as x tends to A, my fx tends to this height. And this height is fa, right? As per the graph. So let's define limits first. And for that, first I'll define left-hand limit. So and the left-hand limit of a function fx at a given point A is written in this manner. Limit x tending to A from the negative side means this one, from this side. If this is point A, then from this side, so we represent it with A negative. This is the left-hand limit of a function fx at point A. And what does it mean? It means, where does my fx go? Let's say I take a sequence x. If instead of this, I take a sequence an, which is less than a, and an converges to a. So I'm taking any sequence an, and it's converging. Any means any. I can choose any sequence. So if there is any sequence that converges to a, and that sequence is less than a, then my f of an so let's say I'll write it in this manner: for an converging to a, where an is less than a, fan, or I should say for all sequences an, By this I mean for all sequences an. For all sequences an that are converging to A. So if there is any sequence that converges to A and that ANs are less than A, then FAN should converge to, and let's say FAN converges to L, then I say this means the limit of fx as x tends to A from the negative side, from the left hand side, is L. Which means, let's take an example and then you will understand. Let's say you have fx is equals to x plus or 2x plus 5. If this is your function and I have to find the limit x tending to A or x tending to, let's say 1 from the negative side, then what does it mean? If there is any sequence an, so first condition on an should be that it should be less than 1, right? And an should converge to, so for any sequence, for any an such that an is less than 1 and an is converging to A, where does FAN go? Or not A, I should take 1 here. 1. Where will this thing go? AN. So what kind of sequences can I take here? I need to take a sequence that is less than 1 and it converges to 1. Can someone give me a sequence that converges to 1 and it's less than 1? You can take AN. There are infinitely many sequences such that its terms are less than 1 and it converges to 1. But I'm giving you one example. It will be this 1 minus 1 by n. If I take this sequence, this converges to 1, right? And this is always less than 1. So my AN is always less than 1 and AN is converging to 1. This is one such example. So you have to make sure that for every sequence, if there is any sequence whose terms are less than 1 and it's converging to 1, for such sequence, your FAN, where is this thing going? That will be the limit of your function. This limit L will be this limit. Let's see where this is going. If I'll take any sequence, let's take this one only. Or for this one, we know very clearly. If you'll have 2, 1 minus 1 by n plus 5, where is this thing going as n tends to infinity? This is FAN, right? Remove it from here. Then my FAN will be 2 times 1 minus 1 by n plus 5, right? Where is this thing going? This is going to 0. This is going to 1. So this entire thing will go to 1. This in brackets will go to 1. This entire term sequence will go to 2. This will go to 5. So 2 plus 5 will go to 7. So this entire thing will go to 7, right? And this is true for all. We've done this thing where if you have 2, if instead of this thing, if I just take simply a sequence, I've taken a very particular sequence just for you guys to know what kind of sequences are allowed when we're trying to find the left-hand limit. So if you're trying to find the left-hand limit at point 1, then all sequences that are allowed here are these ones. AN such that AN is less than 1 and AN tends to 1. So you can only take those sequences here. So if I already know, let's say this is given to me that AN is less than 1 and AN converges to 1, then 2AN, this is FAN, right? 2AN plus 5, because I have to make sure this is a particular case of such sequence. I want to make sure that this is true for every sequence. This limit is 7, no matter which AN I choose, not a specific one, right? So for any AN, any sequence AN, such that AN, the terms are less than 1 and AN is converging to 1, your FAN will be 2AN plus 5. And where is this going? So we'll first use the scalar rule. If AN is going to A, 2AN should go to 2A. AN is going to 1, 2AN should go to 2. And because this is going to 2, this is a constant sequence, it's going to 5. So 2 plus 5 should go to 7. This thing should go to 7. Right? So for any sequence whose terms are less than 1 and that sequence is converging to 1, your FAN will converge to 7. That means fx as x tends to a from the left hand side is 7, because for any sequence that converges to a from the left hand side, the limit of fx is 7, right? That means for any an converging to a, and from the left hand side I can simply write this as an are less than a. It's from the left hand side. That means if this is your a and I want an to converge to a from the left hand side, that means it should be like this: a1, a2, a3, and it keeps coming closer to this point, right, from the left side. My FAN is converging to 7. This implies fx, the limit of fx when x tends to a from the left hand side is 7. Is this clear? The left hand limit thing.
Yes, ma'am.
Similarly, we do the same thing for the right hand limits. So for the right hand limit, we say that fx, this is the notation, as x tends to a from the right hand side limit, this is equals to L if for all sequences an converging to a and an is greater than 0. I want an to converge to a from the right hand side. That means I want this thing to be 2, a1, a2, and then this thing, right? I want this is a3, a4. So I want these terms to be approaching to a from the right side. So I want them to be greater than a. So for all this, if for all the sequences an such that all the terms of an are greater than a, and it converges to a, FAN converges to L. This implies limit of fx as x tends to a from the right hand side is L, right? For example, let's do this example. Let's say you have your function, you have this function, and then I have to find fx as x tends to 2.5. Just 1 second. And I say that the limit exists. This was right hand limit. We have discussed right hand limit and left hand limit. And we say limit of a function at a point exists if fx as x tending to a from the right hand side and limit fx as x tends to a from the left hand side, if both of these are same, then I say that the limit exists. And this same thing is called the limit of the function. And limit of function fx as x tends to a is L. So for example, let's say if you have 1 by x square, if I have fx is equals to 1 by x square, then the limit let's say I take a sequence an, let's say I have to find the limit as x tends to 0. So because I have to find the limit at 0. So first I'll find the left-hand limit. What's my left-hand limit? I have to take an less than 0 and an tending to 0, right? So this will be, if this is true, an is tending to 0 and an is less than 0, then f of an will be 1 by an square. Now, no matter whether an is negative or positive, because you have a square here, this term will eventually be greater than 0, right?
Yeah.
This is greater than 0 and it's decreasing, so this is going to 0, right? This will go to 0. And if you, so this implies limit x tending to 0 from the negative side of fx will be 0. One second, this will be infinity. This will be infinity and this will be infinity too. If your if your an is going to 0, then 1 by an goes to infinity. 0 from the positive side, I should say. Right? Or even if you plot the graph of this, it looks like this. So from this side, you have this thing. It goes to plus infinity. Or if you don't want to get into anything, you can just simply take numbers and you'll notice. If you have 1 and then 0.1 square, 1, 0.01 square, 1, 0.001 square, you'll see this thing, right? Just try to solve these things. You will have 0.01, so this will be 100. This will be 10 to the power 4. This will be 10 to the power 6. And it keeps increasing. And where is this thing going? 100, 10 to the power 4, 10 to the power 6. It keeps increasing. That means it's going to infinity, right? Even if I'll take negative here, I'll have minus 0.1 square, minus 0.01 square, minus 0.001 square. This will still be 10 to the power 4, 10 to the power 6, 10 to the power 2. This is still going to infinity. That means no matter whether you take it from the left-hand side or from the right-hand side, it's going to infinity, right? Similarly, if I'll take it an greater than 0 and an tends to 0, then fan, which is 1 by an square, will go to infinity. This means limit of the function from the positive side to is infinity. And because from the negative side, from the left-hand side and from the right-hand side, both sides, it's infinity. That means your limit is infinity. But if I'll take this one, let's say I'll take this is left-hand limit, this is right-hand limit, and this is the limit of your function. If the left-hand limit and right-hand limit are same, then your limit of function exists at that point, and that is equal to these two limits because they're equal, right? And if they do not exist, let's say, if one of these limits does not exist, if I say limit fx as x tends to a negative, this a from the left side, if this does not exist, that means limit does not exist. Limit of fx as x tending to a in general does not exist. Or a positive. If any one of these two limits does not exist, then that means your entire limit of the function does not exist. And if both of them exist, left-hand limit exists, right-hand limit also exists, but they are not equal, then we say limit of fx does not exist. So if one of them does not exist, that means limit does not exist. If both of them exist, but they're not equal, that again means that the limit of the function does not exist at that point. Okay, let's do this one then. 1 by x. If you have this, let's take an here. An, first we'll take a sequence. And remember that this should be true for all sequences that are negative and they're converging to 0. Right? Not just one sequence that you will take. For example, in this particular case, we have taken a particular sequence. But for all an such that an is less than 0 and an is converging to 0, this thing should be true. Then is when I say that fx is going to infinity, when x is going to 0. Now, if I'll take this thing, let's first do it for the left-hand one. So fx as x tending to 0, negative. For this one, I need a sequence an, which is less than 0 and an converges to 0. So let's simply take a sequence which is less than 0 and it's converging to. Can I take, I'll take 1 by n. Can I take minus 1 by n? If I'll take minus 1 by n an, then this sequence is less than 0 and this is going to 0, right? So I'm choosing this sequence. Then my f of an will be 1 by an, which is minus n. Now when n tends to infinity, where does your minus n go? It tends to minus infinity, right? So that means your left-hand limit is at x is equals to 0 is minus infinity.
Ma'am, I have a
Yeah.
doubt.
Yes.
So left hand it is then x value should be negative.
Yeah.
And we already have a minus 1 by n. So it should tend to positive infinity.
We don't have minus 1 by x. We have 1 by x, right?
I don't mean that. I mean the sequence a by n equal to minus 1 by
Oh,
n.
okay, okay. That's not what we've done. What we have done is you have to choose a sequence an less than 0 such that an converges to 0. Can you give me a sequence that is less than 0 and it is converging to 0? This is the example of one such sequence. If I'll have minus 1, minus 1 by 2, minus 1 by 3, this is converging to 0 and the sequence is negative, right? Less than 0. That's why we've taken this example. Now, if I substitute it here, if I'll find f of an, this is also a sequence. If I'll find f of an, this will be 1 by an because your function is 1 by x, and this will be an's value is minus 1 by n, which gives me minus n. So when n tends to infinity, my minus n tends to minus infinity. What's the problem?
So if we take left hand limit, then the limit should tend to positive infinity because of the minus sign in before of n.
If you take left hand limit, okay, what should I take? As per you, what should I take here?
You should only take an equal to 1 by n.
Okay, let's say I have a 0 here. For the left hand limit, I want a sequence from this side, which converges, which keeps coming closer to 0, right? If I'll take 1 by n, that is a sequence from this side. Is that okay?
Okay, yes.
Okay. So your left hand limit will be minus infinity. Then coming to the right hand one, for right hand, I take an greater than 0 such that an tends to 0, right? So I can take one such sequence that will be 1 by n. Now you can take an to be 1 by n. Example, an is equals to 1 by n. Now my fan will be equal to n. And when n tends to infinity, this will tend to infinity, right? Fan tends to infinity. That means limit fx as x tends to 0 from the positive side is infinity, which means your graph of 1 by x also looks the same. It looks like this. When you approach to this x is equals to 0 is here. When you approach it from this side, your y goes to plus infinity, but when you approach from the left hand side, your fx goes to minus infinity. Here. So your function suggests the same thing, and our calculations also suggest the same thing, right? That means the limit at this point, what's the limit at 0 then?
Not defined.
Not defined. So I can say 1 by x, limit x tending to 0 does not exist. So we have seen an example where the limit does not exist because the limits are different, simply because this limit is different from this one, right? Okay, so is anything left? Yeah, we were discussing this one, right? So this was the step function. This step function is where you take this from 0 to 1. You will have 0 value. Then from 1 to 2, you will have 1 value. This point is excluded, 2 point is excluded. From 2 to 3, you will have 2 value. This point is excluded. From 3 to 4, you will have this value, right? Now, if you have to find the limit at 2.5, so 2.5 point is here. Yeah, this is 2.5. Then if I'll approach this point from this side, where is my function's height going? If I look at this thing, my function's height is this. Let's say this is a sequence that I've taken, which is converging to 2.5. This is any sequence that's converging to 2.5, right? Then the height, where's the height going at these points? It's eventually coming to the height at 2.5, right? Forget about everything else. If you have, this is 2, this is 3, and this is 2.5. And if you have a constant function here from 2 to 3, that means this function is simply you can just simply take this to be fx is equals to the height here was 2. 2. When x is between 2 and 3, right? So when my x goes to 2.5 from the negative side, then my function's value remains 2 because it's constant from 2 to 3, right? That means my fx is simply 2. If I'm here, then fx is, if I'm here, fx is 2. If I'm here, fx is again 2. Here, fx is again 2, 2, 2, 2. So at all these points, it remains 2, right? So where is it going? Or with the way that we have done it, if you have an converging to 2.5 and an is less than 0, less than 2.5, then what is f of an? And when we do this thing, when we say an is converging to 2.5, our main focus is on the points that are close to 2.5. We have to take the points close to 2.5 because it's a sequence. So we'll have points very close to 2.5. That is where our focus should lie. So when you're trying to find the limit at a point, your entire focus should be in the very close neighborhood of 2.5. We don't care what's happening at these points. Is this clear? So that means in close neighborhood of 2.5, here, what's happening here? When we're very close to 2.5, in that interval, what's happening? What is f of an then?
Two.
It's 2, right? This is going to be 2. That means f of an as n tends to infinity, this limit is just 2 because each value is 2. So here you will have limit equals to 2. But now if I'll have, let's say if I'll have fx limit x tending to 3, which is an integer. So if I'll choose an integer, this time I'm trying to find the limit at this point. So when I approach this point, 3 point from the left hand side, what should be the limit?
2.
So from here you have the limit 2. And from the other side, your fx limit is this thing. When x converges to 3 from this side, from the right hand side, your fx is here. The height on this side is this. Right? These are the heights. And this is height 3. That means here you will have 3. And because these two are not equal, that means your limit of fx as x tends to 3 does not exist.
Ma'am, I have a question.
Yeah.
Ma'am, supposedly if in a question we are not told that we need to find, if it is told that we need to find limits of a particular function, but we don't know what do we need to have a corresponding value, as in corresponding to what? We don't know about that. How do we find answer to those questions?
Okay, you've been given a function, right? For
Yes,
you
ma'am.
to find the limit, you only need two things. One is you need a function, and then you need a point, right? So this is what I need. So if you've been given both things, then you can find the limit, right?
Ma'am, but I am
What's
not
not given?
given the value of a. If, I'm sending one of the assignment questions in the chat. If you could have a look.
We can take up the question. We'll have next class where we'll take up the questions. For
Oh,
now, we're
okay.
only, if you have a particular question, we can discuss that. What's the question?
Question number 2. It's actually the lecture. Sorry, I'm just sending it in the chat.
Okay. Meanwhile, we can have a look at these ones. If you have been given a graph like this, let's say you have a function, which is this. And this is your line. This is point 0, 5, let's say. And this keeps coming closer to this line. This is your function fx, curve for fx, and it keeps coming closer to this line. Then what's the limit of fx? As x tends to infinity. That means as x keeps increasing, x increases on this side. As x keeps increasing, where does my function go?
5.
Function means the height of the function. So it's going to 5, right? Because it keeps coming closer to the height. Y is equal to, this line is y is equal to 5, because your height keeps coming closer to the height of this function, this thing. It keeps coming closer to 5. That's why your function is going to 5. And have you shared the question?
Yes, ma'am.
Okay. Can you dictate it to me? It's 3n square. What is it? You have been given a sequence 3n square plus. Can
Plus
someone
5n
dictate
plus
the
2
5n plus 2?
upon 6n square plus 2n plus 1.
So there are tricks to do questions when you have something like this. You know that both of these are, your leading coefficients are n square, right? So the simplest thing to solve this thing is, because if you will have the limit of this will go to infinity. If you will have the limit of this is also going to infinity. So when you have such cases where both the limits are going to infinity in the numerator and denominator, and if you see something like this, infinity by infinity, or if you see 0 by 0 form, or if you see 0 into infinity form, that's also a problem. if you see 0 to the power infinity, if you see these type of forms, there are ways to solve that question. So the first one is, because this one's a simpler one, you can just divide this entire thing, the numerator by n square and the denominator by n square. So nothing changes, right? If I'll divide the numerator by n square, I'll have 3 plus 5 by n plus 2 by n square. And in the denominator, I'll have 6 plus 2 by n plus 1 by n square. And then I can find the limit, right? So this limit is, this goes to, so my an hasn't changed, but the numerator and denominators have changed, right? So this goes to 0 as n tends to infinity. This also goes to 0 and this goes to 3. That means my entire numerator tends to, this entire thing goes to 3 and the denominator goes to 6, right? This thing will go to 3 by 6, which is 1 by 2. Okay.
Okay. And when will we be able to discuss the other parts, infinity by infinity, as you showed here, 0 by 0
This-
or 0 into infinity?
We'll do it when we do the questions. So we'll have a class tomorrow. We'll schedule one class tomorrow and we'll do the questions tomorrow.
Okay.
But we'll try to cover possibly all type of limits. So that's that. I think that is all that we have in this week. Does anyone have anything else to ask?
No.
Okay, so that means we can end this session here.
Okay, ma'am.
Okay.